The decision tree method that we worked with during the previous session represents a powerful approach for moving beyond the consideration of linear relationships among variables into a context of prediction based on exploring how many variables can predict a particular target or response. As we have seen, an advantage of decision trees is that they are easy to interpret and visualize and can potentially uncover patterns in our data that cannot be easily identified through traditional regression methods. However, we've also shown that small changes in the data can lead to different results, and we've explained that while easy to interpret, decision trees are not very reproducible on future data, often making them less useful as reliable prediction models and more suitable for exploratory data analysis and interpretation. In this session, we'll review a related machine learning method known as random forests. This data mining algorithm is based on decision trees, but proceeds by growing many trees, that is, a decision tree forest, in ways that directly address the problem of model reproducibility. Like decision trees, random forests allow us to make binary splits in our data that create segmentations or subgroups by applying a series of simple rules or criteria over and over again, which choose variables that best predict our target variable. While decision trees proceed by searching for a split on every variable in every node, random forest searches for a split on only one variable in a node, the variable that has the largest association with the target among candidate explanatory variables, but only among those explanatory variables that have been randomly selected to be tested for that node. That is, first a small subset of explanatory variables is selected at random. Next, the node is split with the best variable among the small number of randomly selected variables, not the best variable of all the variables, as is true when we are interested in creating only a single decision tree. Once the best variable from the eligible random subset of variables is used to split the node in question, a new list of eligible explanatory variables is selected at random to split on the next node. This continues until the tree is fully grown, and ideally there is one observation in each terminal node, uniquely explained by all of the decisions that came before it. With a large number of explanatory variables, the eligible variable set will be quite different from node to node. However, important variables will eventually make it into the tree, and their relative success in predicting the target variable will begin to get them larger and larger numbers of votes in their favor. The growing of each tree in a random forest is not only based on subsets of explanatory variables at each node, but also based on a random subset of the sample for each tree in the forest. This process of selecting the random sample of observations is known as bagging. Importantly, each tree is grown on a different randomly selected sample of bagged data, with the remaining out-of-bagged data available to test the accuracy of each tree. For each tree, the bagging process selects about 60% of the original sample, while the resulting tree is tested against the remaining 40% of the sample. Thus, the randomly selected bagged data and out-of-bagged data will be a different 60% and 40% of observations for each tree. Finally, before we start to grow our first random forest, I want to mention that the most important thing to know when interpreting the results of random forests is that the trees generated are not themselves interpreted. Instead, they are used to collectively rank the importance of variables in predicting our target of interest.